Welcome to another session of real analysis class. Today we will discuss about limit superior and limit inferior. I'm having a definition here. Definition. Subsequential limit. Subsequential limit. A real number. A real number that is the limit of a sequence. That is the limit of a sequence that's the limit of a subsequence of a sequence xn is called a subsequential limit. A subsequential limit of xn. We use the letter capital S to denote the set of all subsequential limit limits of the bounded sequence xn. So what does this mean? Subsequential limit. Subsequential limit means, suppose we are having a sequence. Here we have got a sequence x. I'm taking my xn. Okay, so I'm taking this x as xn. That xn is equal to, suppose I am having this as 1 minus 1 1 minus 1 1 minus 1 etc. Now it has got a subsequence. What is that? I can form this subsequence as some x dash, and that x dash is equal to 1 1 1 1 extra, right? Now this is a subsequence. Now if you're finding limit of this subsequence, limit of x dash, that's equal to limit of xn dash, right? So limit of this is 1. Now we will say that this 1 is a subsequential limit of this sequence. Similarly, you can go for the subsequence minus 1 minus 1 minus 1 etc., and that will converge to minus 1. That's also another subsequential limit. Now we will collect all these subsequential limit and form a set. That set is called S, and that is denoted by S. Thus, we will examine some of the subsequential limit of sequences. Now here we can note one thing, that the set S is bounded. S is bounded because what is the reason? The sequences are bounded, so subsequence is also bounded because the sequence is bounded. So we can say that such a sequence is bounded, so our set S is also bounded. Now example, consider the sequence xn, that's equal to minus 1 raised to n plus 2 by n. This is the sequence given. Then the subsequence, x2n converges to 1. x2n converges to 1. So x2n means x2, x4, x6, x8, etc. This is the sequence x2n, right? So x2n means this is sequence, and this is equal to what is coming as x2. I will get this as x2. So whenever I am having here x2, my n value is 2, right? So minus 1 square, I will get it as 1, right? So this x2n, I am having the first term as minus 1 raised to 2, that is 1. So 1 plus 1, I am getting 2, first term. Second term x4 again, this is 1 plus 1 by 2. So 1 plus 1 by 2, am I right? Next term, when I am putting 6, again 1. So this is 1 plus, another term is 1 by 3, right? Next term is 1 plus 1 by 4, like that. So this term will become 2, 1 plus 1 by n, 1 plus 1 by 3 plus 1 plus 1 by n. So the general term is going to be is the third term, right? So this can be written as 1 plus, this 2 can be written as 1 plus 1 by 1. So general term of this is an. If you are writing, an should be 1 plus 1 by n type. Now this will converges to 1 as n tends to infinity. So this subsequence will converges to 1. So you can go for another subsequence also. And the subsequence x2n minus 1 converges to minus 1, right? So x2n minus 1 means you will get minus 1 plus 1 by n, minus 1 plus 1 by 2, minus 1 plus 1 by 3, minus 1 plus 1 by 4, etc., right? So like the term should be there. So that you can easily check this subsequence converges to minus 1. Thus, thus the set of subsequential limit is s equal to minus 1, 1. See, I have checked only with two subsequences. It is having plenty of subsequences other than this, but I'm concluding that this s is nothing but minus 1 and 1. So this you can try. So try it. That is, it is having the set of subsequential limit is only this. No other subsequence will have any other limit if it converges. So that you can check by yourself. Now I'm moving to next example. Second example. Consider the set of all rational numbers. Consider the set of all rational numbers in the interval closed interval 0, 1. The set is denumerable, right? The set is denumerable. Denumerable means either should be countable or finite, or it should be countable, right? The set is denumerable. And therefore, denumerable means either should be finite or countable, I have said. So it should have a sequential form, right? So, and therefore, it can be written as a sequence Rn. Then from the density theorem, we are studying that set of rational is dense in R, right? So density theorem, every number in closed interval 0, 1 is a subsequential limit, right? Is a subsequential limit of Rn. Thus, we have our S is capital S is nothing but closed interval 0, 1. See here what is happening is you got the set of real numbers. From that you take the closed interval 0, 1. Right. Now this set is denumerable, right? It's countable. So you can enumerate the numbers. We're taking the rationals, right? So from this, when you're taking rationals, it should be having a positions, right? So collect that numbers. Suppose this is going to be a first rational number, this is second one, this is third one, fourth one, fifth one, etc. So you can form a sequence Rn as R1, R2, R3, etc. This is a sequence. Now this sequence, then in between whatever the points coming in the subsequential closed interval 0, 1, all are going to be the limits, subsequential limit of Rn. Because if you're taking a member here, density theorem says that if you're taking any open interval containing this point, it will definitely contain the set of rationals, right? So we studied about the convergence of limit 2. So what you are getting is always there exists an xn, right? Suppose here you had selected an number from closed number 0, 1 as suppose I am taking this as 1 by 2, right? Suppose this my point is 1 by 2. Then if you are taking an epsilon neighborhood of this 1 by 2, epsilon neighborhood of 1 by 2, then you can take epsilon is equal to 1 by n also, right? So I will get a sequence 1 by 2 plus 1 by n, right? This definitely a sequence in this closed number 0, 1, right? Whenever I'm getting this 2, it will go up to 1. Then after that, every term should be coming in this fashion only. So every point of this interval is going to be a limit point of sequences. So this entire set will become our set as that is set of one subsequential limit. Next we are having a definition. Three point 4.10 definition. There is the limit superior and limit inferior. A part. The limit superior of xn is the infimum of the set V of V belongs to R such that V is less than xn for at most a finite number of n belongs to n. Finite number of n belongs to n. And it is denoted by limit superior of xn, or on the fashion limit of x, or other fashion we can represent this as limit superior of xn. So this is definition of limit superior. So limit superior of xn is the infimum of the set V. So what is the set V? Set V means V less than xn for at most a finite number of n belongs to n, and it is denoted with, first we are having a set V. The specialty about V is that the members of V are less than xn for, that means a sequence is given, you take the terms of the sequence. Now if you can find a number which is less than a finite number of terms of the sequence, repeat, suppose you have got a sequence here x1, x2, x3, etc. Suppose you have got a sequence here. Now, if you can find a v which is less than or equal to x1, v less than or equal to x3, v less than or equal to some x4, v less than or equal to some x10, then see there is finite number of members. For that finite number of members is less than or it is greater than our v. Now you collect this v, right? Such v's you collect, form a set, that is v1, v2, v3, etc. This set is our v. Now you go for infimum of this set, finding infimum of this set. Now this infimum is called the limit superior, right? Limit superior of xn is the infimum of the set v of v belongs to R such that v is less than xn for at most a finite number of n belongs to n. And its notation is either you can write limit superior of xn or limit sup of x or limit superior of xn. So in the same fashion we can define or we can go for here you have defined as infimum. So in the same way you can go for supremum of v also. So that we have defined in another term b, the limit inferior of xn is the supremum of the set of w belongs to R such that xm is less than w for at most a finite number of m belongs to n, and it is denoted by limit inferior xn or limit inferior of x, or in another fashion you can represent this as limit inferior of xn. So in the same way you are going for a set w such that suppose I am naming this as capital W. Capital W is containing the elements W1, W2, etc. such that this W is greater than our terms of the sequence for a finite number of terms. And it is denoted by limit inferior of xn. Okay, first of all, we have defined limit superior. When you're taking limit superior, you go for terms of the sequence and find some numbers which are less than these terms of the sequence for a finite number of terms. You collect such numbers and take its infimum. You will get limit superior. And limit inferior means you are going for a collection of collection of elements. That element is greater than a finite number of terms of our sequence. Then we are going for supremum of such a set, means that is called the limit inferior of the given sequence. So today I have discussed only two definitions. That is, first definition is sequential limit, subsequential limit, and subsequential limit means we're going for subsequences, finding its limit. If it converges means finding its limit, then that limit we are expressing as in a set. The set is called set of subsequential limit and it is denoted by capital S. And next is limit superior of xn and limit inferior of xn. Okay. Next we are having a theorem 3.4.11 theorem. If xn is a bounded sequence of real numbers. Okay, I forgot to ask you or to tell you, this limit superior and limit inferior are defined in many tests in many forms. So you refer any one of the real analysis textbook. Apart from our prescribed textbook, you can find somewhat easy definition for limit superior and limit inferior. If xn is a bounded sequence of real numbers, then the following statements for a real number x star are equivalent. First condition, x star which is equal to limit superior of xn. So this is the equivalence condition for limit superior. B, if epsilon greater than 0, there are at most a finite number of n such that n belongs to n such that x star minus epsilon is less than xn. X star minus epsilon, there are at most a finite number of n such that, this is a finite number I have written, so that's a correction. That's a finite number of n such that x star plus epsilon, I should consider x star plus epsilon, which is less than xn, but an infinite number of n belongs to n such that x star minus epsilon is less than xn. See, if epsilon greater than 0, there are at most a finite number of n belongs to n such that x star plus epsilon is less than xn, but an infinite number of n belongs to n such that x star minus epsilon is less than n. And C, if um equal to supremum of xn such that n greater than or equal to m, then x star equal to infimum of such that n belongs to, m belongs to n, and this is nothing but limit of limit of um. And D, if S is the set of subsequential limit of xn, then x star equal to supremum of S. So as I have said, in different textbook, they are giving different definitions for limit superior and limit inferior. So in some textbook, I have seen this as the definition. So when you are considering the set of all subsequential limit, then go for supremum of such a set, you will get the limit superior. So this is an equivalence condition for limit superior. First condition says that if epsilon greater than 0, there are at most a finite number of n belongs to n such that x star plus epsilon is less than xn, but an infinite number of n belongs to n such that x star minus epsilon is less than xn. Next what it says is n, right? um is equal to supremum of xn such that n greater than or equal to some quantity m. Then x star is nothing but infimum of such that m belongs to n, and that's equal to limit of And the last one, if S is the set of all subsequential limit of xn, then x star equal to supremum of S. So we want to prove this equivalence condition. The next class we will go to the proof of this theorem, and I'm winding up today's session here. Today we have discussed only two definitions and one theorem. Hope you understood. So thank you for your patient listening. Thank you.